Okay, I think we're going. Hey, everybody, welcome back to Telescope Talk Pro. No, Telescope Talk, not the Pro. Sorry, I'm so used to doing the Pro version. Today, I'm really excited about what we're going to talk about. We kind of have a theme going these last couple of weeks. Last week, we talked with some people from Keck and Subaru about this citizen science project that they're involved in called Panoptes, which we learned that for a not insignificant amount of money, we could get involved with some citizen science initiatives. But when I was at NEAF, I ran across my guest today, Jerry Hubble, no relation. In fact, it's not spelled the same either. And he has worked out a way of doing exoplanet transit light curves using amateur equipment. He is the vice president of engineering at Explore Scientific USA. And before I bring him up, let me just say that I put links in the description box to some of the things we're talking about. I put a link to his PDF file, it's basically a PowerPoint, which I'm going to be referring to a lot. In fact, I'll be screen sharing some of it during the Hangout. But I would encourage you to download it and look it over, because he's gone step by step over how to do this and the equipment and all the stuff that we're going to talk about today. So definitely download that and follow along. He's also written a paper which he just posted on archive.org. The link, the paper, not the link. The paper is also in the link in the description box. That link is a Google Drive folder. It's world readable. If some of you could do me a favor during the Hangout, click on it, see if you can get access to these files. Make sure I set the permissions right so that you guys can get them. And if not, leave me a comment in the chat, and then I'll go back and fix it after the Hangout's over. Hopefully, you should be able to get to it okay and download and follow along with all this stuff. So with no more ado, let me bring up my guest. Jerry Hubble. He's off to the side here. He's in his car.
Yeah, I'm right now is a busy time for my home. My kids are coming home. The dogs bark and all this noise. So I figured this is the quietest place to come.
I've never had anybody. I mean, Alberto Conti, who, if you watch my hangouts from years ago, he now works at Ball Aerospace. He tends to join these hangouts from all kinds of weird places, like in his phone. One time he was driving. So yeah. But this is the first time. So welcome, Jerry. It's good to have you.
Observatory and sat in the observatory to do this, but I didn't think about
it. That's right. We'll talk about your observatory. As I recall from your PowerPoints, it's about 3 miles away in Virginia.
It's exactly.
Yeah.
3 miles away from my home. It's far enough to demonstrate remoteness through the remote connection over the internet, but close enough to get to it fast if I need to do anything.
Okay. Well, let me before I get going too much, I have to say we are streaming on YouTube, Twitter, which is Periscope, Facebook, hopefully now, and also Twitch, I believe. So we are on all of those platforms, and I have this comment aggregator thingy that supposed to show me all the comments from all the platforms, but I will manually check these throughout the Hangout just to be sure. Right now I'm seeing lots of stuff from YouTube. Galaxy is around. It's good to see you again, Galaxy. Andy Cowley, Stream Element. Oh, that's Stream Elements. That's not you. That's a bot. Superluminal, he's here. Frank Kenny and others. So Peter Quinn is here. So thank you guys for joining us, and we hope that you'll ask some questions of Jerry here, because I have been telling you guys on Hangouts in the past. We've talked about exoplanets. We've had people from the TESS mission here. We've talked with people from Kepler. Exoplanet astronomy is exploding, and it actually had humble beginnings. And I've told this story many times. I'll tell it one more time. When I was working at the High Altitude Observatory in the early 2000s, I met Tim Brown, who was one of the first people I ever met doing exoplanet transit curves. He was doing it from the parking lot of HAO in Boulder, and he had set up an F2, I believe, Schmidt camera based on an LX200 mount, and he was looking at HD blah 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 blah, and was able to get light curves. So it was one of the first times I'd ever seen this done. But then it went into space. We had Kepler, we had all of these things, all of these people doing exoplanet light curves from space, finding, as we know, hundreds and thousands of planets. And so fast forward now to we're getting confirmation from big ground-based observatories on the ground, but I never forgot Tim Brown. And it's like, why aren't we able to do this from the ground? I know it's possible.
Mhm.
And
Oh yeah.
so with Panoptes, last week we learned that there's one way of doing it, and now with Jerry today we're going to learn. So Jerry, tell us, first of all, introduce yourself. Tell us where you're from, what you do, and then how you decided to do this.
Yeah. So, like you said earlier, I'm the vice president of engineering for Explore Scientific, and my other job with my science side is I'm the assistant director of the Mark Slade Remote Observatory, which is an observatory we built about 3 years ago. And there's a picture. I think I don't know if I included that picture in here. Let's
I
see.
don't think there's a picture. There's a map, but I don't know if there's a picture.
In the no, I didn't include a picture in this with the observatory, but there's one in the paper. You'll see it in the paper. But anyway, this observatory we built 3 years ago with the help of Explore Scientific. We use our equipment in there. We've got a nice 6.5-inch refractor, Apo triplet refractor, which is our flagship refractor. And we got a G11 mount, and we actually got two refractors on that mount, 102 and a 165. And then we use QHY cameras, so we use pretty much off the shelf, commercial off the shelf. And that was doing exoplanet work. I wanted to demonstrate that you could, like you said, you could do it from your backyard, basically.
Now you just said
And
all of that really fast. Say it really slowly of the kind of telescopes you've got in your observatory.
so we've got Explore Scientific equipment. So if you go to
Right.
explorescientificusa.com, you can find our refractors. And the two that we have in there is the triplet 165 FPL 53 Apo refractor. It's carbon fiber. So that's our high-end telescope, our largest telescope that we sell. And then we've got the 102, which is a 4-inch carbon fiber Apo refractor on top of that for our wide field work. And then we actually have a color QHY 16 megapixel QHY camera, which is like the ZWO camera, 16 megapixel color camera.
And
on the
these
main
are
instrument.
brand names, folks. So if you don't know, QHY is a brand name, and Z. What'd you say? Z what? What was the other one?
ZWO.
ZWO. Those are brand names. So
Right, that's another brand name.
right. So these are just cameras he's talking about.
So, and we've also got a 174 QHY 174 M-GPS camera, which is kind of a special camera that NASA's using to do occultations with, because it's a built-in GPS receiver for high resolution timestamps on the video when you're doing occultations.
Good.
So we have that camera also. But so this stuff you can buy from different vendors, similar equipment to use for this work. I think.
Okay, good. So, and I've got your what is a small aperture telescope slide up now. So you give a sort of a generalized view of what you just said, and
right.
And so, exactly. Okay, good. So, and this is all happening from your work is happening from a remote observatory that we just talked about briefly, but maybe you could give us a little, do you want to give us a little detail on that a little bit?
The Mark Slade Remote Observatory is named after a fellow that was in our astronomy club for a long time. He passed away, unfortunately, in 2015, and he left a bunch of equipment that his wife was originally going to sell off, but my partner, Dr. Myron Wasuda, who's a co-author on the paper, he decided that he was best friends with Mark, basically, and he talked to me about building taking that equipment and just go ahead and build the observatory that Mark had planned on building, but he never got to do. So that's what we did. We built the observatory for Mark, and we named it after him, and it's available for the local astronomy community. Our local club is the Rappahannock Astronomy Club, located in Fredericksburg, Virginia area, Central Virginia, halfway between Richmond and Washington, D.C. That's where our area is, and we've got users actually from our area, and then also all across the country and the world. We've got 3 or 4 people in the U.S. that use our system, and then a couple of people overseas that use our system also.
All right. So when we're looking at the telescopes that are of the, whether they're Cassegrains or refractors or whatever they happen to be, they're generally, but the work you did was based on the assumption that whatever light curves you can get, you must be able to get it from relatively expensive stuff that you can buy off the shelf. And you outlined a lot of stuff that
Yes,
you use.
that's
All of
right.
it's off the shelf.
And it's typically stuff that people that already have. That was the other side of it. If people already buy into this equipment quite a bit of money, but these are the typical sizes that they buy, and they'll have everything that they do pretty picture imaging with that they can do this work with also.
Okay, but there's one. What should we do? Should we talk about how you get started, or should we talk about the diffuser? Because that's one piece of equipment.
Yeah, that's the special sauce that goes into this.
Right. Let's go ahead and talk about that now. So, off the shelf equipment, with the exception of this one thing that isn't, well, it kind of is off the shelf. You can order them.
It is off the shelf. You can order it, although the one that we use now is kind of a special order because they don't make it and put it. They make it on special order, and it's the same price as the rest of them as far as the parameters that are involved with that diffuser. But so we use a diffuser. Do you want to talk about?
Yeah. So the
point
diffuser.
spread function?
Yeah. Let me put that slide up. So I'm going to put the point spread function up. So what we're talking about, folks, is that everything that can be done with a planetary light, exoplanet light curves can be done with off the shelf equipment. You need to buy something called a diffuser, and that can't just be any diffuser. It needs to have a special way in which it diffuses star images, because as you guys know, when you look, let's talk about transit for just a brief moment. When spacecraft and large observatories like Kepler and Keck and other places around the world, CTIO, all of these 4-meter, whatever class telescopes around the world, when they measure a planet transiting in front of a star, they have a degree of precision that is incredibly high to be able to make these tiny dips in brightness. For amateur equipment to do that, and every telescope has something called a point spread function, and and basically all it is no matter what you do, no matter how perfect your optics are, you're going to get a smearing out of the light. You're never going to get a perfect point source. And so for amateur equipment, you need to smear that out even more to be able to detect the dip in brightness. So here is a graph, and I've got the point spread function up now, Jerry, if you want to talk about it.
That's
slide
number
12. Yeah, I have 12.
Okay, yeah. So this is a standard point spread function for your run-of-the-mill star that's on your image that you focus. And basically, amateurs use this full width at half maximum. That's what this value is called, the full width at half maximum, as far as the quality of the image. They use that as an analog for the seeing. So when the seeing is really bad, you take an image, you focus it the best you can, but the light is spread out larger when the seeing is worse, as opposed to when it's really nice seeing and you can focus it really tight. But you'll still have this pattern of the light. So this is basically the magnitude across the pixels. The pixels are on the x-axis, and the magnitude of the value in the light is on the y-axis. So that's what that's, and it's a two-dimensional kind of a cone-shaped affair, not just a not like just a one-dimensional graph like this is showing.
Right, and every telescope has this. Later. Every optical system has this, right? There's no way around
That's
it.
Right. There's no way around it. That's just the diffraction. That's the diffraction limit, basically, is what causes that pattern. So if you see, people have seen where they focus a star really tight and it's excellent seeing, and you can see the airy ring, the airy pattern, the airy disk, right? Where you have the central bright spot, and then you have little rings around it. You know what I'm talking about there?
Yeah, the sort of a.
So that's the diffraction ring. That's what causes this fall off in the light from the center. That's what it is.
Yeah.
So if you go to slide number 16.
Is it raining where you are now?
Yeah, you can hear it. Of course. It's going to make a bunch of noise. I tried to get out of the house to make no noise, but it's going to rain. So.
I love it. Okay,
That's all
great.
right. I'm
Yeah.
talking a lot louder than the rain, I think.
Yeah. Okay. That's funny though. All right. So
So if you
yes.
go to page 16, you can see this is how we measure the light. We use aperture photometry, where you basically have two apertures. You have the center aperture, and then you have an aperture called the annulus, and it's that donut-shaped ring on the outside that measures the background. So the light from in the aperture is made up of the starlight and the background, which is really the atmosphere, the light coming through the atmosphere in the background.
Right.
So we want to subtract that, and that's what the annulus is for. So that's how we do a measurement on one star.
And this is important, folks. So this already looks like an out of focus star field.
Yeah, that's actually a diffused. You can see the little note down there. It's a diffused
Half a
image.
degree diffuser. Yeah. So what does that mean, Jerry? The half degree diffuser, and this is what you need to get if you want to do this photometry yourself.
Yeah.
So
So if you go down to, let me see here. Thought I had the picture of it. Okay, so if you go to slide number 34, we'll jump ahead to slide 34.
Whoa, went too far. Here we go. Slide 34. Got it.
All right. Now see, that's what the actual pattern looks like when it's with the diffuser. It's a top hat shape is what it's called. You can see that it's flat across the top and it's got steep sides as opposed to that point spread function we saw earlier where it was a Gaussian shape and you had a peak. This is what the diffuser does. It creates this profile so that, one, you can spread the light out. Now, the importance of, let's talk about this for a second. The importance of spreading the light out is to measure anything accurately, you need as much data as you can get. And what we're trying to do is collect as many photons as we can get, okay? So think about this. Typically, in a normal focused light star image on a CCD, we collect maybe, I'm just going to make a ballpark figure, probably 100,000 to 200,000 photons in let's say it's a 1 minute image, okay, of the star. And it's about halfway exposed, or the exposure is such that the peak is about half. It's not overexposed. It's only about half exposed. It's not up to the peak of the exposure. I'm not explaining that very well, but it's basically you could double the exposure and not saturate it, basically. So it's important not to have saturation. But so when you have a normal star image, it's about 100 to 200,000 photons. But when you spread the light out like this, you're basically lowering the peak, right? The peak height goes down because the total light stays the same, but you're spreading it out. So it's basically allowing you to expose much longer and to collect a whole lot more photons. And we're talking a difference between like 100,000, 200,000 photons up to 10 million photons.
So all we're doing is we're spreading the signal out among more pixels.
More pixels.
And
right.
you can see an image of that in the lower right, where you can see what the out of focus. It's not out of focus. It's diffused.
Not out of focus, it's diffused.
It's diffused. There's a difference.
It's got that 3D shape.
Right.
What's shown on the graph there.
So you got this. So where do you? Let's talk about the diffuser. Where do you get one? And is it a? Are they expensive?
They're as far as the expense, they're in the ballpark of normal other filters like narrowband filters and photometric filters. They're $300 to $400 is what they are.
Okay, so for the price of an expensive filter, that's about what the triads cost from OPT. So
yeah. Right.
So
it's not your standard lunar filters or anything you get for beginners.
Okay.
Like from Celestron or Meade or anything like that. These are photometric type filters.
Okay, so with a off-the-shelf telescope with off-the-shelf cameras and this diffuser spreading the light out, what next?
All right, so you wanted to know who we bought it from. It was a company called RPC Photonics.
RPC Photonics. I should have.
It's in the paper that's from the archive paper that's on.
Oh, okay, good.
Shared, so it's in there. People can find it there. But it's RPC Photonics and based in New York, in Rochester, New York.
Okay.
They designed it, and this is called an engineered diffuser because they actually use a laser to etch the needed pattern into the into the substrate, and you can see. All right, so if you go to slide number 30.
Okay. It's up.
So this will talk about. This is from the original paper that I discovered back a year and a half ago, or a little over a year ago.
Okay. So the diffuser is just in the optical train like you would put it in any other filter.
So you can see that little micrograph. It looks like a dimpled flat plane. It's a bunch of dimples.
Right below
That's what the diffuser looks like.
Okay. And so really it's just a really coordinated way to spread that light up in a very specific pattern without losing as many photons as you can. So, right?
Right.
Okay.
Right.
Okay. So and I think you also have, let me just show this. I think you also have a photo of it. So let me show that photo. I'm going to show slide 35 real quick.
On 35?
Yeah. So here it is in a filter wheel. And
yeah, that's the first filter wheel we installed at the 1 degree, and it was the S-Big camera. We used 2 different cameras during this test. One was an S-Big ST2000, which is a real old camera, and then we moved to the QHY camera.
Yeah, so that's what they look like, folks. They just fit. They're designed to fit into either a filter wheel or in maybe even in an eyepiece holder or whatever it is you're mounting in between your camera and the focuser. So
right now, as a special note, if somebody wants to buy these, they're only going to get the filter itself. They're not going to get a lens or cell.
Oh, you'll just get the piece of glass.
Yeah, you just get the piece of glass. You have to cannibalize one of these cells from some other filter and install it into that.
But they are in a standard filter size, right? So you can just
it's a 1 inch. Yeah.
Okay.
It's a 1 inch. It's actually a tiny bit smaller than a standard filter, but it still fits in a 1 1/4 inch filter. Cell.
Okay. All right. So you could buy one of these for about $400, and then you can cannibalize an older filter, get the ring out of it, so you can mount it in a filter wheel, and you're good to go. So that's the hard part, folks. I know that's a pain, but that's you got to have this.
Work you have to do, yeah.
Yeah, but you gotta have this superluminal. You're cracking me up. He's commenting, is it raining or perhaps it's a meteor shower?
It's raining.
Yeah, it's funny. Okay, so let's see. Hi, Uncle Bill. You're on Twitch. It's good to see you there. And all right, so we've got our telescope. It's not, if you're an imager, this is stuff that's not new to you or hard for you. And then you've got a diffuser set up. What you have outlined a procedure for doing the processing. Should we talk about that now? Oh, actually, I want to show slide 36 real quick.
Okay, yeah.
Yeah, let me show.
That's a good example of what it looks like.
Yeah, this is what, once you've got the diffuser in, this is what your field of view will look like.
It looks like out of focus stars, but it really isn't. They're just diffused.
And you need to do aperture photometry on this. And in this case, you use something called Astro Image J, which I put a link to that software package, which is open source, I understand. The link to that's also in the description box. And that's what will let you do the aperture photometry,
processing
right?
Of the image. Yeah, the aperture photometry.
Okay, all right. So that's what it looks. What your star field will look like when
Astro Image J is geared towards creating light curves from any images that you have. Basically, it doesn't have to be exoplanet light curves. It could be asteroid light curves. It could be variable stars. It could be anything. So it's a good package to get.
Yes, and it's free. Actually, you do have a picture of the observatory. It's slide 39. And
oh yeah, there it is.
There it is. So there's what they're using, folks, to get all this done with. Which is it? Is it the larger refractor at the bottom, or are you using the guide scope for it?
No, the top one is the 102, the 4-inch refractor. It doesn't look 4 inches; it looks a lot smaller. But
it does.
The 6.5 inch, the large one is a 6.5 inch refractor, and the small one on top is a 4-inch refractor.
Now, is using something like a reflector is going to hurt you any on this, like a Schmidt-Cassegrain or something?
Well, that's an interesting question. We did see, if you look in the paper, I discussed this a little bit, where my partner Dennis Conti, who's the AAVSO exoplanet chief of the exoplanet section, he used the C11, which has got a central obstruction, of course, and he found that the diffuser didn't create as perfect a profile like ours does, like we showed on slide 34, how nice and flat the tops were.
Right.
The central obstruction of a reflector causes not quite as good a flatness, I should say. It doesn't look quite as squared off. Okay. But that was the only difference we saw with using his scope as opposed to our refractor. So I think a refractor is probably marginally better than a reflector in that regard.
Okay, but I mean, but we're talking a 4-inch refractor here. We're not talking, super
Right.
giant refractors anyway. So
Now the main thing too to talk about is we're talking about bright stars. We're talking about stars between 6th and 11th magnitude. Okay, relatively bright stars compared to what professionals are looking at 20th magnitude stars. 15th to 20th magnitude. We're talking about nearby bright stars, which is really the primary focus for the test mission.
okay,
And
I
that's
want to
what
get to
drove
that
me.
in just a moment. But before you're starting to segue away from the equipment and toward the
Right.
processing, so that's great, and I definitely want to get to that. But just to finish off with the equipment, this stuff,
Okay.
all of it with the and John Suffol's already commented $300 to $400, and you don't even get the metal bit on the outside. Well, these these
That's
are
because this company doesn't make astronomy filters. They make laser filters for optics engineers and scientists.
and super lumina goes. I like how his guide scope is bigger than my main refractor.
To tell you the truth, we don't use that as a guide scope. That's not a guide scope. That's just our second wide.
You just have it mounted on top of the other scope.
That's right.
Yeah.
Exactly.
Okay. All right. Well, I guess we should talk a little bit about you make a really good step by step procedure, starting at slide 44. I'm going to put that up now. This is all in the PDF file, folks. So I'm not going to leave it up for too long because it's got a lot of words. But it goes through. There's two things in here. It tells you got to get your raw images, you get your the calibration images, and then you use Astro Image J to do the photometry with the aperture photometry. But there's something in here called Maxim DL. It's a piece of software that is used to acquire the images. I put a link to that in the description box as well. You got to buy that, but if you're an imager, you probably
this is the process we use specifically, but you don't. But Astro Image J also does calibrations.
Oh, okay. So you could probably get away with a lot of this.
Astro Image J to do your calibrations. You don't need Maxim DL. We just do that because that's what we use to run our observatory, and it's easier for me to do that with Maxim DL than it is to try to do it with AIJ.
Okay, so what I want to spend a little more time on, now you've got your images, you've acquired them, you've gotten a target. I want to focus a little bit on slide 45, where you go through some of the determine the basic exoplanet parameters from the model fit. Now, once you've got your photometry, you're looking at a star, and you're saying that for this technique to work, it's for the brighter stars, closer by stars, and I assume the larger planets, right? Things like hot Jupiters, or
so that gets to talk about the results and what we got in our results for precision, but we can talk about that a little bit. But yeah, typically hot Jupiters are the first ones you're going to go after. The easiest targets are what you want to start with.
Right. And what are the easiest targets? Give us some examples.
For example, in the paper, I think it was WASP HAT 51 WASP 51. I can't remember the name of it actually. And then because the couple that we did initially weren't really the easiest.
Okay.
They were they were I got to get into a little bit how you measure exoplanet depth. So everybody's familiar with the magnitude scale, right?
Well, enough enough to know that that's a logarithmic scale for measuring the brightness
of brightness, right?
Right.
So
of stars.
What we're doing is we're measuring changes of 1 to 2% changes in the light and the brightness, basically is what it comes down to. So a 1% bright. So when you go to percent, that everybody understands what a percent change is. We're talking about the equivalent to a 1% change in the light is equal to 10 millimags. Okay, that's and a millimag is 1/1000th of a magnitude, or a 0.1% change. Okay, so a 1% change is equal to 10 millimags. So that's what we refer to it in the paper. So the brightest exoplanets that are the brightest stars with the biggest exoplanets that are out there are probably around 7th, 8th magnitude, and the light curve dip, the light changes can change up to 2 to 3%, which are the easiest ones to do. Now we didn't start with that one. I guess we were just kind of a glutton for punishment. But the very first transit, we measured the full transit back in January of 2017, had a depth of 7 or 8 millimag, which is a little less than 1%.
Okay,
It's very challenging. Typically, when you do just normal variable star observing with the image, you can do it with your eyeball, but if you're doing imaging to do variable star measurements, and we're talking about variable stars that change in magnitude, half a magnitude, which would be 500 millimag, and your precision or your accuracy, precision needs to be around 1%. So that's the precision for those measurements at the best is 1% for normal measurements. But we're talking about measurements down to 2 to 3, 4 times smaller than that in this regard, because our light change is very small. It's only a 1% change in light as opposed to a 10% change in the light, let's say.
Yeah, and so because some of these transits, this can get complicated if you just expect to do the transit method on a night, right? You're only gonna, if you expect to see a transit dip over the course of one evening, you're going to be looking at a planet that's in one of those, what do they call, short period exoplanets, where they just, their orbits are measured in hours. So you're going to need to be in this for the long haul, folks. You can't just expect one on a night of observing to look at this star and go, oh, there's the dip in brightness. This isn't like watching Io go across Jupiter or something. You're going to need to really be into this for the long haul, and that's why robotic observatories and observing programs are especially important here. And I am so into this myself that this is what I want to set up here in my own property, whether it's Panoptes, which I am going to do, or something similar to this, where I'm just setting up a program, a systematic program, where I'm looking at these exoplanets over a year, 2 years, 3 years. Because think about it, some of these exoplanets are probably have periods of hundreds of years if you're thinking about a planet like Jupiter. And so to capture those, you're going to really need to be in this for the long haul. So this is a commitment, but it's one that I think is the future of amateur astronomy, in the same way that citizen science and these programs that are out there are something you can get involved in. This is something you can do as well. And if you've taken all the pretty pictures you want to take, if you've looked at the Orion Nebula, you want to look at it, and you want to do something a little bit more in depth, this really appeals to me, because who knows, you might even discover, well, I don't know if you discover any new planets, but you might, and you certainly confirm exoplanets that need confirming.
That's the thing. The scientists have all this high-dollar equipment to do discovery, but they don't have the time and money, actually, or the proper equipment to do the follow-up work, per se, because their stuff is so expensive. It takes a lot of effort to schedule and long time to schedule observations, where that's a perfect job for amateur astronomers to do follow-up work.
And yeah, that's my point. And so they can do candidates. That's certainly what TESS does, and that's what Kepler did before it. But it takes ground-based work, and a lot of it, to confirm these exoplanets. And this is where you and I can come in. Okay, so I want to pick up where we left off. We've got the equipment, we've got the diffuser, we've been taking some images, we've calibrated them, and we've used Astro, what's it called? Astro Image J to get some data. Now I'm going to put up slide 45, which you had up, which sort of takes it from there. This is the interesting part. This is where you're gathering exoplanet catalog data from the Exoplanet Transit Database. Explain slide 45, because I think this one's important. And who's
All
Astro
right, so
Dennis?
yeah, so there's two sources for catalog data that have all the parameters that you'll need to determine what exoplanets you want to look at, what's available to observe tonight or next week or whenever you want to observe. That's all in these databases. There's two of them. The Exoplanet Transit Databases was started about 8 years ago, and it's in the Czech Republic. So it's kind of an odd bird to bring up, because this, if you look up ETD or Exoplanet Transit Database in Google, you'll find the English language page. But if you go anywhere else on the site, it's all in Hungarian.
Okay.
So that's what's interesting about this page. And then you'll find pages that have the exoplanet data, but it's still in Hungarian. And I guess that's what it's called, the language.
Uh-huh.
But
Okay.
the other one is the NASA Exoplanet Archive, which is actually, in some respects, better. But amateurs have been submitting data to the Exoplanet Transit Database for years. So if you want to see what other amateurs are doing, you can go to that and look at that.
All right, that's something to learn about for sure. And then NASA's Exoplanet Archive, and enter the data into the model. What does that mean?
Right. So there's some slides later on, but AstroImage-J has a feature where it'll model the light curve. So once you process the data and analyze the images, it gives you a chart of your data points, right, over time.
Okay, I'm showing slide 46. I don't know if that matters.
Yeah, that's a good one.
Okay. So this is
So that gives you an
AstroImage-J.
idea. That's right. It's AstroImage-J. So you can see the plot behind the main, the front screen, which is the modeling dialog box, and that allows you to enter basic parameters that the star parameters and the planet parameters based on the previous observations. So they've previously modeled this data, or they've previously analyzed all the data from the scientists and the amateurs and come up with specific modeling parameters to use to help fit your curve. So what the model does is you're trying to fit your data to the expected curve, okay, to calculate the time of eclipse, the central time of eclipse, the start time and the stop time, and the slope.
And this is all within AstroImage-J. I just want to
all within
reiterate.
AstroImage-J. That's right.
Okay.
Now there's a little bit of a learning curve, and if you look at the slide previous on 45, there's a link to Dennis Conti's AstroImage-J guide.
Yeah, I also put the link to that in the description box too, guys. By the way, I just want to correct you, Jerry, and both of us. Carol Nowak is saying that the language is Czech, so that's the language from Hungary. Okay.
I just know it's in Hungary.
Yeah.
But yeah, so the modeling, this gets you gives you a starting point to help model your data to see if your data even comes close to what is expected, basically, of that specific planet and sun system.
Okay. Good. So start with Astro Dennis and check out his guide before you get too far.
Yeah, that goes step by step through how to do all this stuff. It's a great guide.
Good.
It's basically the guide he uses when he teaches his AVSO course on exoplanet observing.
Okay, great. And John Suffel, I just want to say to you, he was asking, I have an app that tells me when the Great Red Spot on Jupiter and the main moons are due to transit. Is there any program that will tell us when exoplanets are due to pass in front of the star? And that was those two catalogs we just told you about. Okay.
Yeah, that's on the PC, but I think there is actually a phone app. If you look up exoplanet on your phone, on Apple or Android, I'm sure you'll find a lot of apps that have these data sets in them also.
Oh, all right.
They may even tell you predictions for when the transits occur.
Awesome. Okay.
I haven't done that, but I'm sure you can find them. I'm sure they're out there.
Okay. All right. Well, there you go. There you go, John. All right. Good. Well, all right. So I have a feeling that AstroImage-J is going to be intimidating to a lot of people.
Yeah, it is. It's pretty complicated.
But let me just put up a screenshot that you have of HATP 16. That's a slide 47 on your PDF file. You've done some. This is how you enter the model data.
Yep.
Okay. And what you end up with, there's in a couple of slides. Where did my cursor go? Here we go. A couple of
So if you look at
slides.
50, I think slide 50. No, not
Yeah.
50. Where's it at? I thought I had the chart for at P50. I don't guess I had the 16. The one that's on slide 46 in the background is had P16.
Yeah.
That's the more accurate plot. I thought I had that at a full screen of that chart up in my slides, but I don't. It's in the paper.
Yeah, no, but there's another one. There's another example of HAT
Yeah, this is
P30.
the first one. So HAT P30 WASP 51b.
Right.
The very first one we observed back in January of 18. And you can see the scatter, and you can see that red line drawn through the scatter, the dip in the light. That's the model fit for that particular observation.
And that, okay, how many observations are in here? This is a lot of observations.
How many data points?
Yeah.
There are
and it looks like
probably
it's
close to 100, probably 80 or 90.
and over the course of how long of a period of time?
This is a 4-hour period.
Wait a minute. You got a dip and bright. You got it. This is so you're looking at a short period planet then.
Yeah, this is that's typically the big Jupiter planets are close in. They have an orbital period of, like, our year is only like 3 or 4 days. So they only take like a couple hours to pass across the face of their sun.
Okay.
And we try to get data at least about an hour before and an hour after is what our goal is.
Okay. So this is a short period exoplanet here.
Yeah.
And
the same thing with HAT 16b, which is in the paper. That's another short. So the ones we've looked at so far are really short period because there's a lot more opportunities to observe and to refine and the main thing when you're first starting out is to refine your procedures and your methods and train yourself, right?
Yeah.
So you want as many opportunities as you can to observe. So every 3 days we could observe this star, and it's not exactly 3 days. It's gonna move a few hours back and forth depending on. You may have 2 or 3 opportunities for the next couple weeks, and then you may not have an opportunity for 2 weeks, and then it'll come back because of the period does not match our day length exactly, of course. So
now is the aperture photometry that you're doing on this, is it manual or automated? Do you have to manually open these apertures and get the flux out of them?
No, it's automated.
Good,
So
thank goodness.
You set up the apertures, you set up all the parameters to do the measurement.
And Astro ImageJ does it. Okay.
And it creates these charts. It does everything for you.
Good, because I don't want to be doing those circles.
You got to get all the parameters right. That's the only thing you're trained. That's really what you're doing is you're setting it up to do that work for you.
Okay. All right. And that's in that guide, right?
That's right.
Okay, good. All right. Well, I just need to go. I want to go to the next slide, which is 52. How do you get this? This is apparently off of the Czech site, I guess.
That's right, Czech. So this is an example of that website. So the very first one we did back in January of 18, we submitted it to the Exoplanet Transit Database. Okay, and if you go back to 51, slide 51.
Okay.
They took a spreadsheet of data that we submitted and they plotted it, and this is the plot that they came up with on slide 51. All right, that matches our plot on page 50 on the thing. So page 50 and 51 are basically the same. They're the same exoplanet data.
Okay, so this is what Astro ImageJ puts out. This is what they sent you back from the spreadsheet in this.
Right.
And then this slide here.
And the next one. This is another graphic that they create from our data. So this is what So on the left, that's the catalog geometry, which means this is what the consensus is right now, based on all the measurements. This is what it looks like as far as the planetary system goes and how it crosses in front of the star. And then the cool thing is on the right is our measurement. And
the little shaded areas on top and bottom are like your error bars.
That's all right. That's our error bar. So you can see we did a pretty good job.
That is nice. And then the upper right is just a comparison with Jupiter.
Right, exactly.
What would it be like if Jupiter were there? Okay. Wow. All right. And what
that was a cool thing to see this kind of graphic.
So you sent this website the observations, the photometry, the aperture photometry. They generated this for you.
Yep.
Okay. All right. And is this something that is like anybody can do, or I mean, is there like an interface for it?
You have to create an account like anything else,
Right.
and then you can submit data, and it'll plot it for you, and then you can either. So they do that. They let you do that up front, so you can take a look at it and refine your data. If you see something wrong or something with the plot, then you can go back and work on it and submit it and use it as another tool to see what it looks like. And then once you're satisfied with it, then you can submit it to be stored in their archive as an official observation of that exoplanet.
Okay. So let me just just to reiterate what we're talking about. I did find P16, hat P16. It's on slide 57. There's your light curve. And then the next slide though is
oh, there it is.
Yeah, that's hat 16 or P16. And then the next, why is it not going the other? Why is it not moving? Oh, darn it. Slide come on, man. My computer's not, it's going really slow right now.
What's that?
I said my computer has now suddenly decided it's not going to advance the slide.
Oh.
I really wanted to show that slide. There it goes. Okay. So, and this is where the next slide says modeling results for exoplanet hat P16b. This is what the model. This is the model result. Where do you get this? Where does this come from?
This comes from AstroImageJ.
Okay.
This is on that one dialog box where it showed the model. So there's parameters we enter. There's parameters that it measures off the data, and then it creates these values.
Okay.
The measured values for the planet parameters.
Okay, and I just want, because guys, I want to be complete as possible. There's a screenshot of where those. There they are. This is where it came from the planet, from the software. This is slide 47 for you, Jerry.
47, right?
Yeah,
exactly.
and this is the model parameters that the program that the software generates. So it tells you what the model of the exoplanet is and of the system is, and you get this other. You feed that into the Check website, and you get the model diagram that we saw earlier. So okay, so there we go. So that's a brief tutorial. I'm running really quickly out of time, but I want to talk about TESS. And there's something. What was it called again? There was a TESS. Will you tell us what was it called again?
The TESS is a transiting exoplanet survey satellite.
Yep.
And then Kepler came before that. Is that what you're asking about?
No, there was a program. What was it called? Shoot.
The Transit Follow-Up Program.
That's it. That's the one.
TESS Follow-Up Program.
That's what I'm trying to get you to talk about. Yeah, the
TESS Follow-Up Program. That's so when they created the TESS mission, a big part of it was to be able to get ground-based telescopes involved with the follow-up work, and they not just professionals, but also amateurs involved, because they knew they were going to have a lot of candidates to look at and to validate, and there's no way there's enough professionals to do this work, so they need the amateurs to start to do this work for them and help out to understand where the candidates. And I think part of the reason that they went with the closer, brighter stars, let alone, it's more exciting when you discover an exoplanet that's only 10 light years away or 50 light years away, because man, we could go there. That's the kind of thinking that you might have, like Star Trek, and
somebody could go there, not us.
Local star systems that you can discover planets on, and that's why you want to go to the brighter and closer stars, and that just lends itself to amateur work, because our smaller telescopes can handle these brighter stars, and we're talking about magnitude 6 through 11 or so.
Right, and so this follow-up program that TESS has got going, you get that from the TESS page, the MIT page.
TESS follow-up. There's actually a TESS follow-up website.
Oh.
If you type it into Google, you'll find it.
Okay. Yeah, so this will be so everybody's complaint about TESS is that it only looks at each sector in the sky for 2 months, which means that it's biased toward the short period planets. It might be get the beginning of a
Yeah,
light curve, might not get anything out of a light curve if it's a slow planet. So, but it does look at the entire sky all at once, which is huge.
right,
That's a big
right,
plus. So these kinds of follow-up observations are important because TESS can't get to all of them. Now, if the mission goes longer than 2 years, which I think everybody's expecting it will, then it'll go back to these sectors and get some more data. But here's a way, folks, for you to take these test candidates that are in the brighter star range, and TESS looks at the closer stars anyway, and do some follow up work. And to me, this gets me going because I love imaging. I do. But if you listen to the Space Junk podcast, you know that I'm a visual guy. I don't really care. I mean, I've seen pretty pictures of everything. They're great. It's fun to do. But once you've done it, you've done it. And
right, exactly.
that's my view on imaging. And I know everybody else feels differently about it. But this this
This
is
is the
cool.
exciting discovery type. I mean, personal discovery, not necessarily first time discovery, but personal discovery and personal.
To
You may
see
be the
that
only one
dip
looking at that
myself on
planet.
my computer that I did, oh my God, man, that is
Yeah, you may
like,
be the only one looking at that planet at that time in the whole
that's
world. You may be
right.
the only one observing that object.
Oh man, that gets me going. That gets me up in the morning. And so this technique, download Jerry's paper, download this PDF file, go look at Dennis's Astro Guide on how to use Astro Image J, and do this. Try it. I'm gonna do it. I'm gonna get some equipment from hopefully OPT, but we'll see. Maybe Explore Scientific will give me some stuff, and I can set this up and we'll do it together and we'll
Yeah, that'd be
do
cool.
some exoplanets uh uh light curves here together on online as a stream or whatever it is. So
Well,
oh,
just to get you started, we could always do an observing session at the MSRO. We've got it all set up already, and we could maybe do a broadcast with that. We did that.
that what let you
Scott and I
know
did that previously.
I'm sorry, you did that what?
Scott Roberts, the president, and I of my company, Explore Scientific,
Yep.
we did a Facebook live feed back in November, observing. Actually, it was Hat 16B that I was doing that night when we had. So I was talking to people and doing that observation at the same time.
Would you
Uh,
would you be willing to do that with me? I mean,
sure.
I would love to just go through a night going through this process so
Yeah,
that we could all see how it's
yeah,
done.
that'd be a great example of to show people exactly what's involved.
All right, and I'm going to go look at the live stream you did. Is it still available on Facebook?
Yeah, it's available.
Okay, well, I'll go check that out too, and I'll once I get the link, I'll post it in the description of this one. I'm a big YouTube guy, so everybody follows me on YouTube. I think that'll be my biggest audience. When we were at Times Square, for example, after NEAF, I streamed from Times Square, and that was a big deal. So that was fun. So I'd like to introduce my audience to what you're doing as well. So look for that, folks. I'll talk with Jerry. We'll work it out on a good night, maybe when it's okay with him, and we'll do a stream from his observatory and do it there. Let me get to a couple of questions. Superluminal. So the bigger the aperture, the better. I think that's always true. He's asking. So the bigger the better.
Well, it
The aperture, the
depends.
better.
Not necessarily.
Huh?
Think about what you get when you get bigger aperture. You got more light, right?
Right. More photons.
Now you got to shorten up your exposures to not overexpose your images, and that's really a big part of what the diffuser is about. Is for larger telescopes, and this was done on professional scopes to begin with. That's what the original paper was about. To get on really large telescopes on the brighter stars without saturating the image, because they have to do really short images with a 100-inch or 200-inch telescope. Your images are going to be less than 1 second for a 10th magnitude star.
That's a good point.
Right.
So I
And
think
it's very hard.
and I think the real issue between using a reflector / Cassegrain type, Maxitov, whatever it is, versus a refractor is just the secondary. Apparently it messes up the diffuser.
That's right. That's a small issue. I'd like to investigate it further, but we've actually got a 12-inch Meade LX200 as our second station at the MSRO that we're going to add a diffuser to do testing. So we'll be able to do testing on that
Okay.
in the future.
Okay. So just to finish his comment, Apo refractors are nice, but would they be best suited for exoplanet transits? And I think the consensus is yes. But as Jerry just said, the disadvantage of a secondary isn't that overcomable.
Well,
It's
and the other
something.
thing is, it doesn't have to be a high dollar refractor. I mean, think about what we're doing to the light anyway. We're diffusing it,
Yeah.
right? We're making a splotch.
Yeah. So pristine optics aren't
So
exactly.
pristine optics aren't maybe not the primary thing. I've never done it, but I'd have to look and see what the real difference is. It may not be any difference at all. Now, the key thing is to use a monochrome camera, okay, with the diffuser. You don't want to have a color camera, although our camera is a color camera. What we do is we bend by 2, which combines all the colors into one monochrome pixel. So that's how we get away with it by using a color imager. We bend it by 2 to make a monochrome pixel.
Okay. Rick Schwartz is commenting, I've been to that site many times. I am part of the TESS FOP, but cannot find the presentation being shown on this show. It's in the description box. There's a link, a Google Drive link. Click on it. It'll take you to a folder. In that folder should be 2 files. One of them is Jerry's paper, the archive.org paper, and the other one is this PDF file that I've been showing. So let me know, Rick, if you, in this right now in the chat, if you can get to it. I'll make sure the permissions are right for you to get at. So that's what we've been showing. The presentation in this show, that's where I put it. Hopefully I got the permissions right. Hopefully OPT can give me some stuff. It's good to be Tony. Okay, let me just say they probably won't. But it doesn't hurt to ask. And if I got it, it would be temporary. So yeah, it's not
The link in the presentation is on page 10. To the test follow-up.
Let me go there. Program. Let me go to page 10 and show it real quick. Yes, there it is. Okay, so there it is. Test. So it is on the MIT site /follow-up. And of course, Astro Dennis has his guide there. I didn't know he was from AFSO. That's good. The American Association of Variable Star Observers.
Yeah, the chief of the exoplanet section, and there's a great course that I took back in 2017, the exoplanet observing course that Dennis gives every so often, and he walks you through the process that his guide goes through. But you can, if you're up to it, you can go through the guide and teach yourself quite a bit. At his website, he provides example data to use and to do stuff, to learn it. It just takes a little bit of time to get through, that's all, and some effort.
Okay. All right. Well, let's see. So Rick Schwartz, where is the description box? Oh, Lordy. Well, I don't know. What are you using to watch this with, Rick? I should probably have asked that. It's on YouTube. Every video has a description box. That's what I'm talking about. But Peter Q just said that he sees the PDF, but not the Google Drive. I might have put a link straight to the PDF file. I will add the paper as soon as this Hangout ends to there as well. So, okay. All right. Well, I will stop it there because we're out of time. Jerry, thank you for taking time out in your car in the rain.
I appreciate the invitation to come talk with you. I really enjoyed it, the interview, and look forward to the next time.
Yeah, well, let's follow up with maybe a night observing at your. We'll stream from your observatory.
Yeah, I can. I'll remote in and bring up the screen, the desktop, and then I can share that with you, and then you can broadcast it.
Yeah, that sounds like a plan. We can definitely do that. Okay, Jerry. All right. Well, my guest today was Jerry Hubble. He is the Vice President of Engineering at Explore Scientific, a company that is a telescope retailer, but does a lot of other great things. And I ran into Jerry at NEAF, and we talked about. Actually, I didn't run into him. I actually sought him out because I knew he had done this.
Yeah, you said, I don't know if you saw my talk or heard about it.
I heard about it. I didn't see it, but I heard about it, and so I looked you up, talked to you about it at the booth, and then I knew we had to do a hangout. So thanks for taking time to do it. We will work out and keep an eye out for a future link where we do the hangout from his observatory, and we'll work out some of these kinks. And if you join us, you can ask questions directly to Jerry to find out. Well, if you're having trouble or problems, or if you don't understand something, this will be the chance to work it out because we need to get involved in doing this, folks. I really feel strongly about it. So So I think exoplanet research is the future of amateur astronomy, at least as far as science goes. And I'm excited to get started. So, okay, enough of that.
Yep.
Thank you, Jerry. And thank you
Thanks
guys
a
for,
lot.
huh? Yes.
Thanks a lot.
You're welcome. And thank you guys so much for watching. And as always, keep looking up.